Hello and welcome. This is the second part in the units and measurements chapter. In the last lecture, we have learned about the system of units like SI, CGS and FPS. We have seen base quantities in different units and we have learned about factors to represent very large and small quantities. In this lecture, we are going to learn measurement standards for length, mass and time. We are going to learn parallax method for measuring large distances. Then we are going to learn about accuracy and precision. And lastly, we will learn errors in measurement. In order that all the measurements around the world are uniform and equal, standards of measurements are defined. Therefore, the meter is defined by taking the fixed numerical value of the speed of light in vacuum to be this much meter per second, where the second is defined in terms of cesium frequency. In simple terms, 1 meter is defined as the distance traveled by light in vacuum during a time interval of 1 by this much of a second. Similarly, second is defined by taking the fixed numerical value of cesium frequency, which is the unperturbed ground state hyperfine transition frequency of cesium-133 atom, to be this much when expressed in units of hertz, which is equal to second inverse. In simple terms, 1 second is defined as the time taken by this much oscillations of light of a specified wavelength emitted by cesium-133 atom. Kilogram is defined by taking the fixed numerical value of Planck's constant h to be this much joule second, which is equal to kg meter square per second, where the meter and second are defined in terms of speed of light c and cesium frequency. 1 kilogram is a mass of cylinder of platinum and iridium that is kept at International Bureau of Weights and Measures. Since it is impractical to define atomic mass in terms of kilogram, another unit of mass is used for measuring mass of atoms or molecules. Therefore, one unified atomic mass is defined as 1/12 of the mass of an atom of carbon-12 isotope, including mass of electrons. Now, what are the different ways to measure length? Micrometer level measurement can be done by micrometer or vernier caliper. Smaller dimensions than that, like atomic dimensions, can be measured by electron microscope. And very large distances, like distances between heavenly bodies, can be measured by parallax method. So now we will see how to measure large distances using parallax method. Now suppose that we want to measure the distance of this heavenly object from the earth. We take two observatories on earth separated by distance b, and we focus these two observatories on this heavenly object. So these two observatories are separated by distance b, and this heavenly object is at a distance d from these two observatories. The line of focus of these observatories make an angle alpha with each other. Since distance d is very large compared to the distance between the observatories, alpha can be approximated as the ratio of b by d. This implies that distance D is equal to B by alpha. Alpha is called the parallax angle and B the basis. Now, having measured the distance of this heavenly object from the earth, we can now proceed to find its diameter. Suppose that the diameter of this heavenly object is D and its distance from the earth is capital D. From the earth, this heavenly object will appear like a disk. So now we can focus our observatories on the extreme edges of this heavenly object. The extreme edges of this heavenly body will form an angle alpha at the observatory. Therefore, the diameter D can now be calculated as alpha times distance of this heavenly object from the earth. Now any physical quantity is measured by instruments and no instrument is free of errors. Therefore, accuracy and precision of measurements can be defined as follows. Accuracy is the closeness of the measurement to the actual value. Precision is the number of decimal digits in the measurement. Now we take an example. Suppose the actual value of a physical quantity that we want to measure is 3.678 units. By instrument 1 we get the measurement as 3.6 units and by instrument 2 we get 3.56 units. We can see that the value of instrument 1 is closer to the actual value and the value given by instrument 2 is slightly farther away from the actual value. The value given by instrument 1 has less decimal digits and value given by instrument 2 has more decimal digits. Therefore, instrument 1 is more accurate but less precise and instrument 2 is less accurate but more precise. Since no measurement is error-free, the question arises, what are the sources of error? The errors can be systematic errors, which includes instrument errors, procedural errors, personal errors. Instrument errors occurs due to the imperfect design of the instrument or wrong calibration of the instrument. Procedural error occurs due to the measurement procedure not being accurate. For example, we want to measure the temperature of a certain point, but that point is not accessible, so we put the thermometer at a distance away from that point. This induces the error in the measurement. This is called the procedural error. Personal error occurs because of the individual bias, lack of proper setting of the apparatus, carelessness. An example of the personal error is called the parallax error, which occurs due to the line of sight not being in line with the measuring device. The second type of errors is the random errors, which occurs due to random fluctuations in experimental conditions. Third type of error is the least count error, which occurs due to the resolution of the instrument. Now, errors in measurement can be expressed as absolute errors, relative errors, or percentage errors. Now, suppose that we want to measure a physical quantity. We choose an instrument, we take n measurements, and we get the value A1, A2, A3 up to AN. The mean value of the measurement is defined as the summation of all measurements divided by the number of measurements. The absolute error in the ith measurement is defined as the difference in the ith measurement minus the mean value. The mean absolute error is defined as the summation of modulus of absolute error divided by the number of measurements. Measurement range is mean A minus mean of delta A to mean A plus mean of delta A. Relative error is defined as the mean of delta A divided by mean of A. And percentage error is defined as the relative error times 100%. Now suppose that a physical quantity is expressed in terms of two or more physical quantities which were measured using instruments that were having errors. Suppose that these quantities was x and it was the sum or difference of two or more physical quantities. So we want to know what will be the error in x given that error in A is delta A and error in B is delta B. Therefore, the error in x, that is x plus minus delta x, is equal to A plus minus delta A plus minus B plus minus delta B. This means x plus minus delta x is equal to A plus minus B plus minus delta A plus minus delta B. Since A plus minus delta B is equal to x, we can cancel that out. So the error in x will be delta x is equal to delta A plus minus delta B, and the maximum value of the error in x will be equal to delta A plus delta B. Therefore, when two quantities are added or subtracted, the absolute error in the final result is the sum of absolute errors in the individual quantities. Now suppose that a physical quantity is expressed as a product of two physical quantities. That means x is equal to AB. Therefore, the errors can be introduced and we get this equation: x plus minus delta x is equal to A plus minus delta A times B plus minus delta B. We can expand it and get x plus minus delta x is equal to AB plus minus A times delta B plus minus B times delta A plus minus delta A times delta B. Since delta A times delta B involves product of two small quantities, it can be neglected, and then dividing this equation by x is equal to AB, we get 1 plus minus delta x by x equal to 1 plus minus delta A by A plus minus delta B by B. Therefore, the maximum error in the quantity x is equal to delta A by A plus delta B by B. This means that when two quantities are multiplied or subtracted, the relative error in the final result is the sum of relative errors in the individual quantities. Again, suppose that the physical quantities is measured as a quotient of two other physical quantities. That means x is equal to A by B. We can introduce the errors and we can get x plus minus delta x is equal to A plus minus delta A divided by B plus minus delta B. We can take the cross products and get x plus minus delta x times B plus minus delta B is equal to A plus minus delta A. We can expand it and get xb plus minus b delta x plus minus x delta b plus minus delta x times delta b is equal to A plus minus delta A, and we can neglect this expression, that is delta x times delta b, as it involves product of two small quantities. Now we divide the whole equation by A is equal to xb, and we get xb by A plus minus b delta x by A plus minus x delta b by A. This is equal to 1 plus minus delta A by A. Since A is equal to xb, we get this expression as 1 and this as delta x by x and this as delta b by b. This means 1 plus minus delta x by x plus minus delta b by b is equal to 1 plus minus delta a by a. And this means that the relative error in x is equal to the sum of relative errors in A and B. Therefore, when two quantities are divided, the relative error in the final result is the sum of relative errors in the individual quantities. To summarize, in this lecture we have learned measurement standards for length, mass and time. We have learned about the Parallax method for measuring large distances. We have learned about the accuracy and precision of the measurements, and we have learned about errors in measurement. In next lecture we will learn about significant digits and dimensional analysis.